You, Christian.
Okay, sorry. Can you hear me? No?
Join audio. You should probably do the join audio.
Okay.
I can hear you.
Okay.
But maybe the local participants can't.
Just a moment.
She's not on our side. Okay.
Robert, can you maybe say something to?
Sure. What would you like me to say? Just for
Okay, so
testing.
it's our fault, so we also don't hear Robert.
Okay.
Okay.
Join audio is a good idea, no? No.
But yeah. Okay. So, but I can hear you, Matthias.
Yes, now we hear
Yeah.
you.
Okay.
Thank you.
Can you hear me?
Yes.
Thanks, Robert. Okay, I guess that I should just start.
Yeah, so
Okay.
I'm supposed to chair. So welcome everybody. Yeah, today's speaker in the seminar is Boaz Klartag, and he will talk about Riemannian rigidity of Riemannian embeddings of discrete metric spaces. Thank you.
Okay, thanks. Hello, everybody. Let me begin by thanking the organizers, Christina Soromani and Robert McCann, for inviting me to speak in this special semester on non-smooth Riemannian Lorentzian geometry. And indeed, as we just heard, I'm going to talk about, first of all, it is my joint work with Matan Eilat, who's a graduate student at the Weizmann Institute in Israel. And I'm going to talk about some Riemannian aspects of discrete metric spaces. I think, I'm not sure, but I think that maybe our framework is not entirely the usual setting in low regularity geometry. If I got it right, then usually in low regularity geometry, people study, I don't know, Alexandrov spaces or these spaces of Sturm and Odd-Villani. And these spaces are non-smooth. But in these spaces, usually when you have 2 points x and y, in many cases, you have the full nice geodesic connecting them. On the other hand, if you have a discrete metric space, just points that are each point in its own neighborhood, then typically the midpoint between x and y is not available to you because it's not in your space. So you cannot easily construct comparison triangles and do things that are, I guess, more common in low regularity geometry. Okay. That said, let me, so understand the rules in this seminar that the first lecture of today is going to be an introduction. So I'm going to proceed with a rather slow introduction to this topic. And please feel free, both the people on Zoom and the people in this class, please feel free to stop me and interrupt me at any time if you have questions. Okay, so what is our setting? Throughout this lecture, M is going to be a Riemannian manifold. In fact, it's going to be a complete, connected, n-dimensional Riemannian manifold. Okay, so for instance, you could think on some surface in R3. That's completely fine example. So if this is R3, then we can try to draw some null surface. Something like, let me try to draw some, I don't know, this kind of scarf is some Riemannian surface, which we denote by M. It is a submanifold of R3. Okay, and what is the meaning of this word complete and connected? Connected means that there is just one connected component. You don't have two separate surfaces. And complete, this means that if you have any Cauchy sequence in this manifold, so if you have any sequence of points whose distances tend to 0, then the limit point is also inside your manifold. Okay, so you cannot, if you take some nice surface in our sphere, a sphere, a torus, a cylinder, and you take away one point, then it's no longer complete because you can tend to this point, but oops, the limiting point is not in your manifold. Okay, so this is complete and connected. Now, given 2 points, x and y, on the manifold, you can look on curves on the manifold connecting them. And each curve has a length. Okay, in the case of a surface in R3, the length is just the length with respect to the Euclidean metric. We all know to measure the length of a curve in three-dimensional space. But the curve is confined to stay on the manifold. And when you take the infimum over all lengths of such curves, you get the distance, d of xy. Okay, that's the Riemannian, maybe I should write the m of xy. This is the Riemannian distance between x and y. Okay, so for any 2 points, the infimum of the length of the curve is the Riemannian distance. And this means that we kind of view Riemannian manifold as a metric space. Okay, it's a completely legitimate point of view to think intrinsically, if you want, on a Riemannian manifold as being a metric space. Okay, so we're interested in embedding. So what's an embedding? So definition, suppose that X is a metric space. So you have some distance function. It could be finite or infinite. We don't care. Then we say that X embeds in, let's say we write, it's more proper. We say that X embeds in M, and we write this symbol if there is a map from X to the manifold which preserves distances. So the distance between for any X and Y, if you measure the distance at X, it's the same as the distance between f of x and f of y on the manifold. Okay, so if you look at this example here, if I don't know, I have a metric space with 3 points, x, y, and z, so then it means that the length of these geodesics, the 3 of them, should be exactly what is given by the data of the metric space. Okay, so that's an embedding. It's f is definitely 1-to-1. Okay, let's begin with a non-example. So which metric spaces do not embed in any Riemannian manifold. So these are branching metric spaces. So I'm given a space X of 4 points. And let me tell you the distances. So these are 4 points. I'm going 1, 2, 3, and 4. And the distances will be maybe, okay, this will be 1, this will be 1, and this will be 2. So this means that if I put them on a manifold, then this point is a midpoint of that curve. But I also make it a midpoint of another curve, like this. And this distance could be whatever you want. 1 as well. Okay, in this case, if I try to embed this example in a Riemannian manifold, what will happen? I'd have a geodesic. So this would be a geodesic. Because this is 1, this is 1, and this is 2. So this point must be in the middle of a minimizing geodesic between these 2 points. But also, this will be a geodesic. Why is the blue geodesic? For the same reason, 1, 1, and 2. So these 2 are geodesics. But in a Riemannian manifold, if 2 geodesics overlap, then they coincide, right? If you begin to go in certain direction on a minimizing geodesic, you cannot just split and get two minimizing geodesics. Okay, so the tangent here kind of points in 2 different directions, which is impossible. So in this case, you don't have any embedding in any Riemannian manifold. So X does not embed in M for any M. Okay, and a space is non-branching if it does not contain 4 points with this property. So a space is a branching metric space if it contains 4 points. So there is some local obstruction for this of an embedding. Branching metric space, so it contains 4 points, which are not collinear. So it's not that you have these 4 points, you cannot embed them in a line, distance being the distance on a line, but they contain 2 collinear triplets. Okay, so that's a non-example. All right, now, sorry, question, anything? Please.
Okay, so you're saying for this branching metric space, the metric space doesn't embed into the Riemannian manifold because
Neither Finsler, by the way.
Huh?
Neither Finsler, not even Finsler.
Finsler, okay. Because like you said, you have geodesics that aren't coinciding that separate. But if you were to lower the regularity of the Riemannian manifold to like continuity, then in that case, you know these property of geodesics, or I mean you don't even have geodesics in that case, and so you could have different length minimizers or something. So is there a statement? Or
So maybe I should emphasize. So the manifold itself is smooth.
Yeah.
The matrix, the non-smooth, if you like, comes from the discrete subset.
Okay, so my question, so the question would be
so
then,
such a manifold, as you say, would have, if it's a manifold, it would have curvature minus infinity or something completely.
Yeah.
If it's a C1 Riemannian manifold, such a picture cannot exist. In a C1 Riemannian manifold.
But even what about a T0, like with just a continuous metric? Could it exist?
In a continuous metric, I have no idea. This is a pathology that I don't know.
And of course, I guess that these branching, you could, I mean, this needs to be a boundary of this manifold because you can embed this example into a manifold with boundary, but that's not what you want, right?
I could not hear you, Robert.
Oh, sorry. I was just
Slowly.
saying that it's important that these manifolds not have boundary because you
Yeah,
could,
without boundary, right. Smooth and no, right, without boundary, right. That's a good, yeah. Smooth and no boundary. Right, sure. Right. Sure, yeah. So we look at embedding into distant Riemannian manifold. If you have a C0 Riemannian manifold, can you get branching examples? I don't know. So would you call this thing Riemannian? So would you call this thing Riemannian manifold? If so, then yes, sure. If this is Riemannian manifold, then this is a branching Riemannian manifold.
no, I think the point of the example of the C0 example was that the geodesic equation solutions exist, but they're not unique. And so then you can get this kind of branching phenomenon. When you want to apply the Picard theorem, the vector field isn't Lipschitz. It's
So in the C0 example, do you have a geodesic equation? Do you have Christoffel symbols? Do you have?
For a C1 Riemannian manifold, you would have the geodesic equation, but you don't have.
You need C11, right?
Yeah.
You need it to be Lipschitz in order to have the uniqueness.
Yeah, so not C11 because that would guarantee uniqueness of geodesics. But so
Right.
just C1, and then you can have branching.
Uh-huh.
And so then maybe this could be embedded into one of those types of manifolds. I don't know. It's just a question.
Okay. Anyway, the Riemannian manifold for me should be
All right,
smooth.
so for you, you're just considering smooth
I would
Riemannian.
not. I mean, yeah.
Okay.
That's. With more questions? Okay. So there is a folklore result. I'm not sure where it's written actually, but the French authors know about it. That if you have any finite metric space, embeds isometrically in a Riemannian surface. Non-branching. in a two-dimensional Riemannian surface. Typically of high genus. Let me explain to you this result in an example. So suppose your space, your metric space, has 5 points. Let's make it without collinear points. So it's actually, this can be weakened to being non-branching. Then how would you embed it into a two-dimensional Riemannian surface? So let's first of all embed it topologically as a graph in a torus. So let me draw a torus. And I put my 5 points here. So as we know, the complete graph on 5 vertices can be embedded in a torus. So how do you do it? So you need this one, and this one, okay? So you can get 10 disjoint curves connecting these 5 points. And now you can basically find a smooth Riemannian metric on this torus, so that this will be the geodesic. You put the metric to be, the tensor to be rather small on the curve that you chose, you align distance correctly, and the metric is huge outside these things, so you get the correct distances. And if you have more than 5, you have 6 or 7, you just need bigger genus. So this folklore result kind of tells you that, I mean, you cannot quite detect that many things from knowing knowing the distance in some set. So even if you take, I don't know, in R3 some net in some big box, I don't know, grid of 100 by 100 by 100, 1 million points, and you look at distances, this still embeds in two-dimensional Riemannian surface. So it does not even detect the fact that it came from a 3D space if you don't restrict the topology. And the question that we'd like to ask is, how about the countable case? So suppose that I want some discrete metric space, but not a finite one. So what about countable metric spaces? And let's start with an example of a countable metric space. So for instance, let's take a net in Rn. So what is a net? X in Rn is a net, or a delta net, sometimes people say, if there exists some number delta, such as a delta net, such that any point in Rn is of distance at most delta from one of the points in the net. Euclidean distance. Okay, this is Euclidean distance. Okay, so a net just collection of points in the plane that nothing is too far from the net. Okay, for example, a lattice. Any lattice is a net. Okay, 2D lattice is a net. N-dimensional lattice is a net in R, because if you have a lattice, then surely, if delta is big enough, then all points are bounded distance from the net. And the question is whether you can, suppose that you embed a Euclidean net in some Riemannian manifold, what can you learn about that manifold? Is it the situation like here that large parts of the manifold are not covered at all by geodesics and you know very little about them? Okay, so a net is a metric space with Euclidean distance. Okay, so XD is the induced Euclidean distance. And our first result is that there's a difference between the finite and the countable case. So suppose that X is a net, and R2 is a net, and M is a two-dimensional Riemannian manifold. Smooth, connected, complete Riemannian manifold. Which contains a copy of X, a symmetric copy of X. Then M is flat. So since M is smooth, it has a curvature tensor, and you can compute it, and it's 0. And in fact, it has isometric to the plane. Okay, so even though you have geometry with lots of gaps, without geodesic, without curves, without tensors, just we have kind of a cloud of points, each one for its own, you can still determine the full Riemannian structure of the manifold if you know the distances on this set alone. Okay, it's not even C0 manifold, it's just some cloud of points. Okay, so this is theorem 1. Let me remark, so any questions? Comments? Yes. I will talk. That's something that we'll talk a lot. Don't worry. Yes. I mean, we don't. Okay. We know it's difformorphic. Yeah.
Can we come back to the theorem for a minute? Yeah. So I don't. Sorry, I can't see that blackboard. If the camera person thinks.
Which blackboard do you want to see?
This one. This is perfect. This is great.
Okay.
So you mean so we embed it? Sorry, you say any finite metric space that embeds in a 2D Riemannian surface.
In a pseudo-Riemannian?
No. Sorry, I'm sorry. I'm missing the punchline again. Where was the punchline? You said if you have
for finite metric spaces, you can always put them on a 2D surface, and you cannot. I mean, there are many different surfaces that embed a metric space. You cannot determine the complete geometry for the metric space. You don't know much about it. For instance, you don't have a finite metric space that requires 3-dimensional spaces. While we'll see in a second examples of metric spaces that do not mean anything two-dimensional because they are intrinsically 3-dimensional, for instance.
Okay. So the point of this theorem is that I start out with a Euclidean net in the Euclidean plane, and then I isometrically embed it into some other manifold. And then the conclusion is that M is flat and isomorphic to maybe isometric to what's the conclusion? I still can't see the blackboard. What's the conclusion on the blackboard?
Isometric to flat R2. Oh, so okay.
Could it not be the torus? I'm confused. Oh, it's not. It won't be isometric in the torus. Okay, I understand. Thanks.
It cannot be a torus. No, it's flat R2. Just
another question. For example, instead of powerful equation, somehow the complete two-dimensional
hyperbolic plane. Hyperbolic plane. Yes. I will discuss this too. You ask questions that will be discussed.
So they will be correct, or sometimes correct, sometimes incorrect.
That's sometimes yes. That's a good question for yes. We'll discuss this. Yes. More questions? Okay, so just to say, yes.
One question. The manifold is smooth here, or it's
It's smooth. It is smooth. Yes, it is smooth. Okay. I don't know if it is C2 or C3, but it is smooth.
Okay.
Okay.
So okay. Thanks.
Okay, so I just want to remark that this is a purely a Riemannian phenomena, so it fails for the Finsler manifold. So if you have Finsler manifold, so you can do the following trick. You can take, this is an example that appears basically in Boaz and Ivanov. You can take the Euclidean plane, you can have some net there, and you can take a disk disjoint from all of these points, and you can perturb the metric inside in a Finsler way. So not Riemannian, but a Finsler perturbation inside the disk, so that all outside distances, all distances from the outside are not altered. So in the first case, there is no hope for such strong rigidity theorems that you can detect the full Riemannian manifold from the discrete set, but in the Riemannian case, it does hold true. Okay, now about, I want to discuss the higher dimensional case. Oh, no, wait, first I want to discuss some corollary. So the corollary is that if X in R3, for example, is some set which is not contained in a two-dimensional, in a plane, but contains some net in some plane, then for any M which is two-dimensional, X does not embed in M. So such a metric space requires a three-dimensional manifold in order to be embedded. So an example is that just take some lattice in R2 and add 1 point in 3 dimensions. So if X is Z2 times 0, and you add to it the point 0, 0, 1, then this has what we call asymptotic dimension 3, because it embeds in R3, right? It's a subset of R3, so it embeds in some three-dimensional manifold. But you add just 1 point to the Euclidean, to the lattice, and it does not embed in any two-dimensional Riemannian manifold. Okay. Now what about Rn? So in Rn we kind of still struggle. Let me tell you what we know. This doesn't answer the question here. So in Rn, so suppose that X in Rn is a lattice, not a lattice, a net. M is n-dimensional Riemannian manifold, complete connected smooth. Such that X embeds in M. So we don't exactly know, we cannot say immediately that M is isometric to Rn, but M is diffeomorphic, at least we detect the topology to Rn. And if n equals 4, that's not the exotic R4, but the flat R4. Okay, so that's a partial result in your towards your question. Let me remark that okay, so there are some cases where we know. Okay, if you add a sum, okay, so this is kind of Matan is exactly working on these things now. Under some assumptions, you get isometric. So for instance, if you know that the metric tensor is compactly supported, it's true. Second remark is that here, this is also, here you don't have to be a Euclidean net for this, the diffeomorphic part of the proof is kind of more soft. And for it, this is more general, and this works also for non-Euclidean spaces. Say for the hyperbolic plane, for some discrete sets, you can also detect the diffeomorphism type. Okay, but I cannot. Oh, okay. Yes, I can. Oh, I cannot really, huh? Let's see. So this should go a bit up. This goes all the way down. Can you see? Okay, I think it's okay. Okay, hi Robert. Hi Bob. Okay. Yeah. So there are also some other partial results. For instance, we know it seems that we know that X would be also a net in the target manifold in n dimensions. There are some partial, but we don't still have a complete answer in n dimensions. The finite case.
Some complete Riemannian.
Sure, yeah, sure you can have, yeah, you can have things that definitely you can have, yeah, you can have, how do you construct a negative result? Take a countable set so that all geodesics miss a certain region in your manifold. If all of them miss, then you can, yeah, no.
No, but assume that this countable set is a net.
Yes, you can have a net. A net so that algebraic miss certain, you put a little mushroom kind of growing from some point and then, yes. More questions?
Can I maybe ask a question? Just about, will you specify more about countable examples? Because a priori your definition of a net does not need, so a net does not need to be countable. Maybe uncountable. So
Yes.
Are countable examples sort of, do they give
A net
nicer results?
is either countable, a net in R2 is infinite. So if it's not countable, then you even have more information. If you know that something uncountable embeds in M, it's only easier for you. You have more information.
So countable is really some interesting special case.
It is the non-trivial case, yes.
Okay.
Yes. Yes, it's not just right. We don't use the fact it's countable. Yes, please. But infinite, it's used.
So for your second remark, you say it also works for some non-Euclidean
Yeah,
spaces.
I cannot be too. Yeah.
So I mean, I can see how there might be an analog for hyperbolic space.
Yes,
for
that's what I'm thinking about. A hyperbolic
but for
plane.
a spherical space,
Sphere is compact.
Yes.
So I'm not quite sure what would be a good formulation in the case of the sphere.
Yeah.
So maybe for the sphere you want infinitely many points in the sphere.
I don't want infinitely many points. I think maybe the analog would be a finite number of points that would still satisfy this net condition.
No, that cannot be, because if you have just 5 points, then there are regions in the sphere that are not covered by the geodesics, and if you modify the metric there, you cannot detect that. So if you have in the sphere just finitely many points, you cannot detect the topology, definitely not the metric of the sphere. So if you just think, let's see, so you have this is the sphere, you have some points, 1, 2, 3, 17 points. So just draw the great arcs for netting them, okay? Suppose now I take a region that is not covered by these finitely many arcs, and I grow a big mushroom, okay? A huge mushroom. Here I put a little statue of Robert, okay. I can do whatever I want on them, and the geodesic would never detect that. Yeah. So yeah. So I don't have a good formulation of this for the. So okay. In general, I think that there is okay. This is, let me just kind of wave hands. There is a finitary effect. So there is an effect that you could see in a finite metric space. What's the effect? If you have, say, finite net, suppose you take, I don't know, all latitude and some finite net, I mean, net of, I don't know, 1 epsilon net in S2. Okay, epsilon net, it has 1 over epsilon square points. Okay? If you know all distances, my feeling is that you cannot recover the full geometry of the manifold, but you do recover geometry in a much, much smaller scale than epsilon. Okay, so somehow I know something in the scale of epsilon square. I don't know. That's kind of, I don't know how to make a theorem that I can prove, but that's the feeling. That for my friend, just gives you a smaller scale. And if you have a net, then okay, it goes all the way to zeros and you recover everything. That's kind of, but that's not math. Just, okay. Yeah, okay. Yeah, where was I? Yeah, okay. So I said that, okay, so yeah, for the hyperbolic plane, things like that, yeah, we have examples of this sort. Sometimes you need more than a net, sometimes less. Okay. It's not entirely done. Not entirely understood. Now I want to make it a bit more formal. So what's a metrically rigid set? So if M is a Riemannian manifold, subset X of M, usually countable, but does not have to be, is metrically rigid if for any other Riemannian manifold, M tilde, of the same dimension, it's very important, if you know the following, whenever X embeds in M tilde, this determines the Riemannian manifold M tilde. This implies that M tilde is isometric to M. Okay, so you have your manifold M, think about R2 or some very specific thing, say, okay. You want subset of R2 so that if you embed them anywhere of the same dimension, then that anywhere has to be the place where it came from. So X really encodes the entire geometry of the manifold where it lies. So for instance, okay, what we just said, yeah, I'm just repeating myself just 20 times, but okay. So what we said is that nets are metrically rigid. Okay, so nets in R2. But also, you know, okay, also other things are metrically rigid, but also, I don't know, if you have a Poisson process, it's still okay. Also, the Poisson process with probability 1. So there is something we call quasi-net, which is enough. Okay. And two questions is first question, do we have metric rigidity for nets in Hadamard manifolds? So this we don't know in general. We don't have a counterexample actually. For Hadamard manifold, so Hadamard manifold means simply connected, non-positive curvature. If you have a Hadamard manifold, I don't know a single example of a net which is not rigid in Hadamard manifold. And second question, just because this is the semester on Riemannian and Lorentzian geometry, so I can ask about Lorentzian. So I mean, I know very little about Lorentzian manifold. So what would be the question? Is it true that what subsets of Minkowski spacetime, what discrete, let me emphasize, discrete subsets, if there are, okay, are there discrete subsets of Minkowski spacetime of Minkowski spacetime that are Lorentz distance or proper time rigid. So that is, if you have maybe I'm not sure, I don't know what's next, but okay. So in Minkowski spacetime or in any Lorentzian manifold, you have a notion of Lorentz distance. It may be infinity many times, but sometimes it's finite. And still you can look at this definition. Just now, instead of M being Riemannian, just think of M being Lorentzian. Is it true that you can detect the geometry of curved spacetime by having some discrete set of, I don't know, spaceships and knowing the proper time between them, and maybe this determines Minkowski spacetime? I don't know. After you're done with Minkowski spacetime, you can look at the Schwarzschild solution or the Kerr solution or other more examples. So I really know nothing about question 2, absolutely nothing. Okay, now I want to tell you about some history questions. Okay, some history. I mean, rigidity is developed.
Does anyone know anything about that second question?
I don't think so. So before we're playing this, so let me, I mean, really, if it wasn't, if the word Lorentzian would not appear in the title of this semester, I would not think about this. So no, I apologize. I don't know enough about, also, everything is in reverse, right, in Lorentzian geometry. Yeah, maybe it does not make sense. And the net, you know, if you have, I don't know, really? This came to Lorentzian metric discrete rigidity? Yes?
Basically, yeah, well, they wouldn't have called it that, but basically, they wouldn't have Lorentzian distance. They're mostly interested in just the causal relations.
Okay, future or past, yeah. And whether it determines mass, determines whether there is a black hole and stuff like that?
That's going too far. I think so. I'm not up on what they do, but I know them and I know of them. So
please connect. I mean, please tell me later. Okay. It sounds really exciting. Yes. Yeah, I'm okay. I know very little. I mean, I took an undergrad class some years ago about general relativity, but other than that, I don't, not an expert. Good, interesting. Okay. Yeah, history, right? I mean, okay. Metric rigidity is okay. So, so I'm not going to survey all rigidity results in mathematics or in geometry. Let me discuss what I think is some amount of development which is relevant for us. And I think that okay, some history of this geometric rigidity, of Riemannian rigidity. So at least rigidity. So the first result I want to mention is from 1948 by Hopf, which is a beautiful paper, very short. So Hopf proved actually more than what I will say, but okay, proves that if you have any Riemannian metric on the torus without conjugate points, I'll explain if you don't, without conjugate points is flat. Okay, so kind of historically, the condition that appeared usually was about what are conjugate points? These are critical values of the exponential map. We say that 2 points P and Q are conjugate if you look at the geodesic between them. In a complete manifold, you have geodesics, and if you vary, let's say, the direction of this geodesic to first order here, then the change here is to zero, is to second order, is to higher order. So this basically, if you change the direction of the geodesic goes, it basically nearly does not move in Q. For instance, on the sphere, antipodal points are conjugate points, because if you look at this geodesic and you now shoot it in a somewhat different direction, you then at exactly the same point. Okay, so these are conjugate points, and formally it's critical values of the exponential map. And Hopf proves that, yeah, if you don't have these conjugate points, if your metric, I would not say it has unique, okay, if they're conjugate, then it has to be flat. It's not just a unique metric, there are many flat metrics on the torus. It's not, you know, you can take any lattice gives you a different, it's not isometric to square a torus, but still it is flat. And it was conjectured it's true in any dimensions. It was work by Weizmann, important on that, but it was solved a bit later. A bit means not a bit, some years later, by Boaz and Ivanov, and they show that it's true in any dimension. Okay, so also on Tn, the Riemannian metric without conjugate points is flat. Now I want to tell you about Michel's conjecture from the 80s. So the Boaz-Ivanov proof uses some ergodic theory, and it is kind of very much tailored to the case of the torus. Well, I hope introduce a technique which was useful also in other cases, and also in some of them I'm going to mention. Now, Michel's conjecture from 81 and the following, this time we discuss Riemannian manifolds, smooth Riemannian manifolds with boundary. So any simple, I'll explain what simple means in a second. Any simple Riemannian manifold with boundary is determined from boundary distances. Okay, so what's simple? Simple is a good important word here. So we have some Riemannian manifold with boundary. Okay, so the manifold is M and it has a boundary. And the meaning of the word simple is that if you have 2 points on the boundary, x and y, 2 points on the boundary, then there is a unique geodesic, minimizing geodesic connecting them, and it is entirely in the interior of the boundary, entirely interior of the manifold M, except for the 2 endpoints. That's simple. Okay, so for instance, if you have strongly convex domains in Rn, these are simple. Okay, strictly is fine. Okay. Strictly convex domains in Rn. And the conjecture says that if you know the distances between all points in the boundary, so this collection of data, this determines M. So any 2 manifolds with the same boundary distances are isometric to each other. Okay, so this is Michel's conjecture for Form 81. Any questions or anything about it? Okay, so it's true in some cases. So it was early, I mean, in the, I think, years ago, it was proven for strongly convex domains in constant curvature. In Rn or Hn or hemisphere. Pestov and Ullmann, an impressive work. This was O2. This shows that it's true in 2 dimensions. Okay, it's still not known in dimension 3. Let me also mention another rigidity result. So this will stay. I cannot move it up. So I should. Is that the minimum? Can you see above that point or even? Okay. Bangert and Emmerich. I hope I pronounce the German name. I hope it. And Emmerich in 13, they proved the following results, which was proof utilizes the Hopf technique. So suppose that M. Okay, first of all, you know it's diffeomorphic to R2. Second, you know that it has no conjugate points. Then, let's pick some point X in M. Then if you look at the area of a disk of radius R around X, if it has no conjugate points, it kind of feels like negative curvature, so you kind of assume it should be more, the volume should be more than what you get in the flat case. This is indeed correct, but it's correct in a rather strong sense. So the limit inf of this, of the disk is at least 1. Better to put the pi there, at least pi, with equality if and only if you're flat. M is flat R2. It's a given plane. Okay. Now I think that I have 11 more minutes until 3. Am I right? Christian, how much? What's the?
Yeah.
Yes.
And yeah, 9 minutes.
5. How much? 9.
Or 5.
Or 5. 5. Okay. Okay. So now
5, so.
I want to tell you a few things about. If there are no questions, I want to tell you a few things about the proofs of our theorems. Other questions? The proofs. So we want to make contact. Okay, so plan of proof. We want to make contact with this body of research about the case where you have no conjugate points. Can you ask? 2013. Ah, it's a recent one, relatively. Yes. And that's 2002. Okay. But 81 is 1981. Okay?
I saw a paper I recently read from the 1980s that had very similar statements, but I can't quite tell.
Okay. From 1980s. Okay. Okay. Right. So our power of proof is okay. So first of all, use the embedding. Okay, embedding x in M, and shows that there are no conjugate points. And well, once you know there's no conjugate points, then you can use large-scale geometry, right? You have a net. So if you know that the net is Euclidean and it's from large scale, it really looks like a flat R2, and you could hope to get bounds on, say, area of disks. And yeah, you can do that and conclude that using this no conjugate point thing, you conclude that it's flat. Okay, so that's the general plan. Let me tell you a few words about part of how to show that there are no conjugate points, part of the beginning of the proof. And the paper is on archive in case you want to learn more. So, so we have a discrete set X, okay, which is, okay, it's both in Rn, let's say, okay, let's do it in Rn because I will not reach the point for you. It's on Rn and in the M. Okay, so the discrete, it's a subset of Rn which is embedded in M, okay? And let's fix some point P in this X, okay? And let's take, consider some sequence of points P M, okay, because then it's taken, Pm in X which tend to infinity. Okay, so that's the picture. So you have P, that's Pm, P1, P2, etc., P3, whatever. And I connect them by geodesics. So in a complete manifold, there is at least one geodesic minimizing connecting any 2 points. And now I take a subsequence of these geodesics from P to P1, P to P2, and this converges to some ray, to a minimizing geodesic ray from P. Emanating from P. Okay. But of course, the geodesic rays that you obtain depends on the sequence that this I mean, okay, there are many sequences. You can take many geodesics. Now let me give a definition. So we say that the sequence of points. So let V in Sn minus 1 be fixed, and suppose that Pm in X tending to infinity. We say that Pm is drifting in direction V, and we do it like this. If Pm normalized to a unit vector tends to V. Okay, so this is the point P, and P, you want these things to tend to direction V. Okay, and what you want to show that this minimizing geodesic ray is determined by V. That's really the very, very first step in the proof. Okay, so if you have sequences going in the same directions, they'll have the same geodesic ray. And for that, we will use one Lipschitz functions. So we will use, we'll use one Lipschitz functions and some ideas from the theory of L1 mass transport. which is probably the only connection to the next lecture today by Chachmak. We also discussed that thing. Okay, so if you have a one Lipschitz function, then you know that the distance between 2 points is f of x minus f of, at least f of x minus f of y. Okay, so this gives you lower bound on the distances, and these things are kind of dual to curves, because curve gives you upper bounds. So if you have a curve connecting x and y, then gives you an upper bound for gamma. And there is a developed theory of one-Lipschitz functions. There is the concept of that I learned actually from the papers by Evans and Gangbu, and Feldman and McCann in the Riemannian case. This is Euclidean, this is Riemannian. 3 years later, and the concept of transport ray. So it says that unit speed gamma from AB to M, unit speed is a transport ray. If the one Lipschitz transport to ray of f, if f progresses in the maximal possible speed on gamma, f of gamma of t minus f of gamma of s is just t minus s. It cannot be faster than that because it's one Lipschitz, but that's the critical thing. And one of the things that I learned from this paper is that if you know, if you have two transport rays that intersect in the interior points, they have to coincide. And two transport rays that intersect an interior point overlap, it's more accurate to say. Okay, so you cannot have a picture like this. So if this is a transport curve, and that one is a transport curve, that's impossible. Because it's like the interior point of one of them, that's impossible. And you use this type of idea, it doesn't explain much. You construct some kind of Boaz function, some ideal boundary, and you show that if you have two sequences that drift to direction v, the geodesic have to coincide because of this fact that we have here. Okay, so I think I'm just 1 minute out of time, so I think it's a good point to stop. And thank you for your attention. For the many questions, thank you also. You can ask more. Okay.
Yeah, thank you very much for the nice talk. Are there any questions?